diagram is a visual way to reconstruct the electron configuration by showing each of the separate orbitals and the spins on those electrons that are in those little orbitals. All right, so basically an orbital diagram is a visual representation of an electron configuration. Okay, so if we take a look right here, we have obviously an atom that appears to have 7 electrons, and so where are those first 2 electrons going to go? They're going to go in the 1s orbital, right? There's 2 electrons that are in the 2s orbital, and there's 3 electrons that are all going to be in the 2p orbital. Okay, so this right here would be an electron configuration for nitrogen. How can we tell? Because it has 3 electrons right here, right? It's got, I'm sorry, it has a total of 7 electrons, I apologize. And so this is going to be nitrogen, right? And so in an earlier video, we learned how to draw or write the electron configuration for nitrogen. It would be 1s2, 2s2, 2p3. And today we're going to learn how to draw these little orbital diagrams that we see right here, a visual representation of the electron configurations that we learned in an earlier video. So before we start drawing the orbital diagrams, let's first take a look at a few little rules that you need to keep in mind when we're drawing these orbital diagrams of the different elements or atoms. Okay, so the first little rule is called the Pauli exclusion principle. And so when we're drawing the orbital diagrams, we have to pay attention to the Pauli exclusion principle. And what the Pauli exclusion principle basically states is that the electrons that are in these little orbitals here are going to be negative. They're going to have a negative charge. And when you get 2 negative particles next to one another and they're very close together in the atomic orbitals, they're going to end up repelling each other, causing the spins of those electrons to be opposite. Okay, so the Pauli exclusion principle basically states that if you have 2 electrons in a little s orbital here, then one of those electrons is going to spin one way, indicated by the little up arrow, and one of those electrons is going to spin in the opposite direction, indicated here by the arrow pointing down. Okay, so if we take a look at the electron configuration of oxygen here, 1s2, 2s2, 2p4, and then we want to write the orbital diagram or draw the orbital diagram for it, this would be incorrect. So why would this be incorrect? Well, if we take a look in the 1s orbital, one spinning one way, the other spinning the opposite way, in the 2s orbital, one spinning one way, the other spinning the opposite way. And if we take a look right here in the 2p orbital, we can notice that in the first little p orbital here, both of these are spinning in the same direction, right? So according to the Pauli exclusion principle, this cannot happen. These 2 electrons are going to have to spin in opposite directions. So this is an incorrect orbital diagram. And if we wanted to fix this, we can see the correct orbital diagram for oxygen right here down below, right? If we take a look, oxygen is going to have 8 electrons. The first 2 are in the 1s orbital, the next 2 are in the 2s orbital. And then if we take a look right here in the 2p's, we've got 4 electrons in there, right? And so in the first p orbital, one of those electrons is going to spin one way and the other is going to spin in the opposite direction. Okay, so understand the Pauli exclusion principle and keep that in mind when you're drawing these orbital diagrams. Let's take a look now at the Aufbau filling diagram. So when we're drawing these orbital diagrams, you also have to pay attention to the Aufbau filling diagram. And what this basically shows us, and it showed us in an earlier video, is the order in which those orbitals get filled with electrons. If we take a look at this little chart right here, electrons will start to fill the 1s orbital. And once that reaches the maximum it can hold, which is 2, it's then going to start filling the 2s orbital. And then once the 2s orbital has a completely filled orbital with a maximum of 2, the next orbital to be filled is the 2p's, then the 3s's, then the 3p's, then the 4s's, then the 3d's, the 4p's, the 5s's, and then the 4d's and the 5p's and the 6s's, and so on and so on. So this little diagram is helpful when doing electron configurations and orbital diagrams in that it allows you to determine which orbitals are going to be filled first before others can be filled. And keep in mind that the s's, all these little s orbitals here, can hold a max of 2 electrons. All the p's here can hold a max of 6 electrons. All the d's can hold a max of 10 electrons. And all the f's here can hold a max of 14 electrons. All right, so there's 2 little rules, the Pauli exclusion principle and the Aufbau filling diagram. Now let's take a look at Hund's rule and then apply these 3 principles to solving a few orbital diagrams of our own, or some examples of some orbital diagrams. Okay, so the third and final rule regarding the orbital diagrams is called Hund's rule, and it basically states that when you start placing these little electrons or arrows which represent the electrons in the different orbitals, it basically states that you must first put one little arrow or electron in each little orbital or box here before you go back and place a second one. So for example, if we take a look right here, here is the correct orbital diagram for nitrogen. We can tell this is nitrogen because there's 7 electrons, and so the electron configuration would be 1s2, 2s2, 2p3, and this is going to be an atom of nitrogen, right? And so this is the correct orbital diagram. This would be incorrect, right? This is the incorrect orbital diagram for nitrogen. Well, why? Well, according to Hund's rule, it states that in this 2p orbital here, you must first place one little electron in each orbital, all spinning in the same direction, indicated by 3 up arrows, before you go back and place a second little electron or arrow in the orbital. So if we take a look right here, this would be incorrect, right? This would be incorrect because we've put 2 into this little box before we've placed 1 into this little box. So the way that we can fix that is to have it look like you see right here. All right, so that's Hund's rule. If we take a look right here, same thing. If we take a look, this is the correct orbital diagram for it appears to be carbon. We can tell it's carbon because it has 6 little arrows or electrons. And this is the incorrect orbital diagram. But let's take a look why. Why is this incorrect right here? Well, there's 2 reasons. First of all, if we take a look, Hund's rule was not paid close attention to, right? If we take a look, we needed to place this one little electron in this orbital before we can go back and put another electron in this little box or orbital right here. So this would be incorrect. Also, this is a down arrow right here. And so according to Hund's rule and the Pauli exclusion principle, if you're starting with one little up arrow and this electron is spinning in a certain direction, then all of the little electrons in the in these little boxes where there's only one, they also need to spin in that same direction. So you can't have an up arrow here and a down arrow here, okay? So understand that concept of Hund's rule, the Aufbau filling diagram, and the Pauli exclusion principle. So let's take a look at a few more examples of Hund's rule and then do some problems of our own. All right, so here's some examples of some orbital diagrams. Let's see if they're correct or incorrect according to Hund's rule. Well, if we take a look, this looks like it's a lithium atom. We have 3 electrons. The first 2 are going to go in the 1s orbital, like we see right here. One of them spinning one way, the other spinning the other way. That's acceptable. And that last one little electron is going to go in the 2s orbital, and it's going to spin in a certain direction. So this is going to be correct. If we take a look right here, this is also correct, right? 2 electrons spinning in opposite directions, 2 electrons spinning in opposite directions. And then right here in the 2p orbital, this one little electron is spinning in a given direction. So this would be correct also. However, this one would be incorrect right here. In this third example, we have 2 electrons in the 1s orbital here spinning in opposite directions, 2 electrons spinning in opposite directions here. But in this 2p orbital, if we take a look, Hund's rule states that this one little electron is going to have to be spinning in the up direction. Okay, so if we cross this out, and if we wanted to correct it, this technically would be the correct orbital diagram for this atom of carbon right here. Okay, and last but not least, in fact, if you take a look, here is the correct orbital diagram for carbon, right? So understand Hund's rule. Now let's take a look at a few examples and do some orbital diagrams of our own. Okay, so let's do some orbital diagrams, and what I recommend is that you pause this video and try this yourself. So we have hydrogen, right? We know that there's only one little s orbital, so it gets one little box, right? There's only one shape of an s orbital, so it has one little box. There's one little electron in there, and it's spinning in a certain direction, right? So this would be the correct orbital diagram of hydrogen. If you ended up doing it like this, that too would be correct. Okay, so either one of these is going to be the correct orbital diagram for hydrogen. Let's take a look at the next one. All right, if we take a look at helium, helium has 2 electrons, right? And so helium, those 2 electrons are going to fill the 1s orbital. One of them spins one way, and the other spins the opposite way. And so here we go. Here's our orbital diagram for helium. And if you ended up putting this would be the same thing. Right? If you end up doing this right here, that is exactly the same thing. Either one of those will be correct. Let's take a look at another one. So we're getting bigger now. Here is lithium. Here's the electron configuration. We learned how to do those in an earlier video. So there's 2 electrons in the 1s. One is spinning one way, the other spinning the other way. And then we have a 2s1. So there's 1 electron in this 2s orbital. It can go like this. In fact, if you wanted to put this as a little down arrow, that would be acceptable also. So there's our orbital diagram for lithium. Okay, so here we have carbon, 1s2, 2s2, 2p2. So in the 1s orbital, there's 2 electrons spinning in opposite directions. In the 2s orbital, same thing. And last but not least, we have 2 electrons in this 2p orbital. So we need to make sure we pay attention to Hund's rule and fill each one of these little boxes or orbitals up with 1 electron first before we can go back and fill the orbital or box up with a second one. So if I were to ask you how many unpaired electrons does carbon have, the only way you'd be able to figure that out is to do the orbital diagram and see that it has 2 unpaired electrons, right? 2 unpaired electrons. So there's our orbital diagram for carbon. If you wanted to put these both as down arrows, that would be acceptable as well. Let's take a look at another one. All right, so here's our electron configuration for aluminum. So 2 electrons in the 1s orbital, 2 electrons in the 2s orbital. We have 6 electrons in the 2p, so we must first place 1 little electron in each one of these little orbitals or boxes before we go back and put another one. We have 2 electrons in the 3s, and last but not least, we have 1 electron in the 3p. And so we can put this right here as either an up arrow or a down arrow.